So this video will finish the review on chapter 8. And so the first part of chapter 8 was about, defining a solution, what is a solute and a solvent. We talked about colloids and suspensions, electrolytes, strong electrolytes versus weak electrolytes versus non-electrolytes. And so here, the type of the arrow used is very important. And then the second thing is, are you making ions when the substance dissolves in water or not? If you're making ions, then it's an electrolyte. But then if the arrow is a double arrow that shows a reversible reaction, then it's a weak electrolyte. You need a single arrow going to the right to show that it's a strong electrolyte. So we talked about the basic solubility rule that is saying like dissolves like, and the property here is polarity. So if it's similar polarity wise, then it will dissolve well, versus if it's polar with polar. So we have that. And then we were arrived at solubility. And so solubility, it's actually meaning a value. It's the maximum amount of solute. Sorry, hold on. So solubility represents the maximum amount of solute that can be dissolved in a given amount of solvent. And so it's a value, and typically it's given for water. It's, there's tables for compounds, common compounds, that give their solubility in 100 milliliters of water at different temperatures. So it's curves actually, because the solubility varies as a function of temperature. And so here in this problem, it's about sucrose. Sucrose is, sugar. So the solubility of sucrose is 204 grams in 100 milliliters in water at 20 degrees Celsius. So we know that at 20 degrees Celsius, when you have 100 milliliters of water, you can only dissolve a maximum of 204 grams of sucrose in that amount of water. After that, what happens is that the grains will not dissolve anymore. And so if you pour more sucrose, then you will have some sucrose left crystallized at the bottom of your container. And so there are terms, saturated and unsaturated, that talk about, the state of your solution. And so unsaturated is when you have less than the maximum amount in the solution. And saturated is when you have reached the maximum and are above the maximum amount. So practically, when you see an unsaturated solution, and because it's made of water, it will look like water, right? Because everything is dissolved. You cannot tell there is something dissolved in it. But when you have a saturated solution, you will see some grains at the bottom of the beaker. It will not be all dissolved because you have reached the maximum, and if you have even more, then that extra amount of solute that cannot dissolve will be crystallized and showing up at the bottom of the container. So you can visually see the difference between these two, but also with numbers. So let's look at these examples. So if you're adding 200 grams of sucrose to 100 milliliters of water at 20 degrees, so classify the solution as unsaturated or saturated. So you can use the chat and tell me if you think it's saturated or unsaturated. Yes, it's unsaturated, and this one is easy to see that because we have the same amount of water and same temperature. Actually, we will always compare to the same temperature. but we have the same amount of water. And here, 200 is slightly less than the maximum, which is 204 grams of sucrose. So we're slightly under, and so it will be unsaturated. Yes. So let's look at B. Adding 110 grams of sucrose to 50 milliliters of water at 20 degrees. So is this a saturated solution or an unsaturated solution? And here you have to think more. Because it's not the same amount of reference of water. Yes, so so the way to see that, so you multiply that 50 milliliter by 2, and so it's similar to adding. So if you multiply the volume of water by 2, then you need to multiply the amount of solute you would put in there by 2. So it is like adding. So 110 times 2 is 220 grams of sucrose in 100 milliliters of water, you know, at 20 degrees. So now we can more easily see that this 220 grams of sucrose is more than the maximum. So the solution is saturated. And here you would see some grains of sucrose at the bottom of the container. Okay, so let's look at C. Adding 350 grams of sucrose to 200 milliliters of water at 20 degrees Celsius. So same thing, think about that. Unsaturated. So again, here the amount of water is not the same. So we need to think about what would it be if it was 100 milliliters of water. So if it's 100 milliliters of water, it means you are dividing the volume of water by 2. So that means you are dividing the amount of sucrose by 2. And so it is like adding, so 350 divided by 2 is 175 grams of sucrose in 100 milliliters of water. And oh, so what do you think? Is it saturated? Right? If you divide the amount of water by 2, and so you divide this by 2, and this is the amount in 100 milliliters of water. So is the solution saturated or unsaturated? Yes. Unsaturated. Yes, it's unsaturated because this is less than the 204 grams in 100 milliliters. So it's less. So we have not reached the maximum, and you could put more and it would still dissolve. So that's what this means. Basically, saturation is when you have reached the maximum you can have, and then above that it's saturated. Okay. And so another word about solubility of solid in a liquid. It depends on temperature, and for a solid in a liquid, the solubility increases as temperature increases. Think about, you know, how it is easier to dissolve sugar in a hot coffee than in a cold coffee or tea. Or salt in water. Salt will dissolve in the water when water warms up, right? So solubility increases when temperature increases. You can dissolve more solid into the liquid when it's warm. For gases, it's different. For gases, it's the opposite. The solubility of a gas decreases when temperature increases. So it's opposite to the solid. let's think about how the solubility of helium gas in water is affected by each of the following changes. So if you are increasing the temperature from 25 degrees Celsius to 50 degrees Celsius, what will happen to the solubility of helium gas? Decrease, yes. As I said, the solubility of helium gas decreases as temperature increases. It's important to remember that it's opposite of what happens to solid. And so then if temperature is decreased from 25 degrees to 0 degrees Celsius, what happens to the solubility of helium gas? Yes, increases. So when the temperature decreases, you can put more gas into a liquid. And that's why, you have more aquatic life in cold temperatures than warm temperatures, even though you have a lot of fish in tropical areas too. But there is much more aquatic life in cold waters, because cold water will have more oxygen in it, right? You know how oxygen is also dissolved in water, and that's how fish, breathe. They filter the water and take the oxygen from there. And so there is more oxygen in cold water than warm water. So that's important for aquatic life. That temperature is not too warm, right? So another thing about gases, the solubility of gases, is that the solubility of a gas, it depends on pressure, which is not the case for solids. Solids, they don't depend on pressure. The solubility will not be affected by the pressure. But for gases, you know how gases are, we saw in chapter 7 how they can be compressed or expand, and so pressure is important for gases. And so the solubility of a gas in a liquid will depend on pressure. And if you increase the pressure above the gas pressure above a liquid, you will be able to put more of that gas into the liquid. It's like you're pushing the gas inside the liquid, and its solubility will increase. And so tell me what happens if you're increasing the pressure from 1 atmosphere to 2 atmosphere. What will happen to the solubility of helium gas? Yeah. Oops, where am I? Solubility of gas. Solubility of the gas increases when you increase the pressure of that gas above the liquid. And so that's how they make carbonated beverages, for example. Carbonated beverages are made with carbon dioxide pushed into the water. So they seal the cans or the bottles with high pressure of CO2 above the liquid, or maybe they bubble it inside, and they seal, and then the can is sealed under a high pressure of CO2. And that's why when you open the can at room temperature, it fizzes, and you see you can hear the pressure being released, right? And so the CO2 escapes into the air, and then that by reaction inside the liquid, you see those tiny bubbles forming inside the carbonated beverage. And that's because the CO2 now becomes less soluble in the liquid, because you have decreased the pressure of the CO2 above the liquid. And so decreased pressure means decreased solubility in the liquid. And so the CO2 will want to escape, and so it makes bubbles that will move up and escape. So yeah, well, I'm saying this before we watch the answer. So yes, the decreasing the pressure from 5 atmosphere to 1 atmosphere would would do what to the solubility of helium? Decrease, yes. Oops. Solubility of helium will decrease when you decrease the pressure above the liquid. You really have to think about, it's like a lot of pressure of gas above the liquid, pushes that gas inside the liquid. It's able to take more. You increase the solubility. Okay, so some more about solubility, but this time it's solubility of ionic compound in water. So we have a special case here, and we have tables that we call solubility rules that are used to predict whether the following ionic compounds are soluble in water. So as a general rule, we were saying earlier that anything that is ionic will be soluble in water, but it's not completely true. Not all ionic compounds are soluble in water. Sometimes the strength of the ions bonded together is so strong that you cannot dissolve it in water. And so we use the solubility rules, and let me show you. So let's look at the first one, MgSO4. And then you will need a table for that. You cannot decide without this table. You have that in your one of the lab. Forgot which one, but one of the lab has these tables. It looks different, but it's gonna tell you the same information in the end. So it's called the solubility rules, and it tells you, depending on the ions that are forming your compound, it tells you if it will be soluble or not. And this first part of the table here tells you the ions that will make soluble compound, and there are some exceptions, so you want to read completely the table before you decide. And then the second part, the bottom part here, is focusing on insoluble ionic compounds. So compounds that contain those ions will typically be insoluble, but there are exceptions. And in the exceptions, typically you will always have, for the insoluble one, you will always have the alkali metal and ammonium, right? And then sometimes the group 2A, sometimes not. So ammoniums and the alkali metal always make soluble compound. Let me remind you what are the alkali metals. Alkali metals are those in group 1A, right? Lithium, sodium, potassium, rubidium, cesium, francium. Typically, they will always make soluble compound. And then ammonium, but ammonium is a polyatomic ion, NH4+. So we had, the first element we had was MgSO4. MgSO4. So MgSO4 is made of magnesium, and SO4 is the sulfate ion, right? We have the table here of the polyatomic ion, and sulfate is there in the middle here. So sulfate is also in that table of solubility rules, and it's in the first part of the table that says soluble ionic compound containing sulfate, the last one here. Sulfate normally makes soluble compound, except when it's with Sr2, strontium, barium, mercury, and lead. And we have it with magnesium. So then what do you conclude? Is MgSO4 soluble or not? So tell me that. Yes, it's soluble. It's soluble, but because magnesium is not part of the exceptions for sulfate. Yes. Okay, let's look at ZnCO3, zinc carbonate. Let's look at the table again. Zinc carbonate. Zinc carbonate. Okay, yes, the carbonate is among the insoluble compound, right? It's among the insoluble compound, and exceptions are with ammonium, NH4+, and the alkali metal, and we have it with zinc. Zinc is not an alkali metal, so yes, and now it's insoluble, right? Because the carbonates are usually insoluble, and zinc is not an exception, so it's insoluble. Okay. LiOH. Oops. I'm just preparing here. So LiOH. Let's look at. So Li. What is Li? It's lithium and OH. Hopefully, you start remembering about the hydroxide ion. OH minus is the hydroxide ion. It's a polyatomic ion. It's an important one because it's what makes a compound basic, you know, the base. So it's one that you want to recognize. It's with lithium. So let's find OH minus here. We found OH minus in the insoluble part. It's making insoluble compound usually. Exceptions, compound of the alkali metals, ammonium, calcium, strontium, and barium. What do you think? Is LiOH soluble or insoluble? Yeah. Li is an alkali metal, and it's part of the exceptions, right? So it's soluble, right? Li is soluble. LiOH, I mean. Yeah, the reason why it's soluble, it's because so OH minus typically makes ionic compound that are insoluble, so it's part of the insoluble, but then the Li is part of the exceptions. It's an alkali metal, right? If you look at the periodic table, Li is one of those group 1A metal, okay? Let's look at the last one. It's, oh, well, there's two more. So CrOH 2 times, so again, with the hydroxide ion. This time it's with chromium. Cr is chromium. So we know already the hydroxide ion makes insoluble compound, and chromium is not part of the exceptions, right? If you look here, chromium is not an alkali metal, it's a transition metal. It's not ammonium, calcium, strontium, or barium. So that means it's insoluble, right? It's not part of the exception, so that means it's insoluble. Sorry, should have asked you. So insoluble. So do the other one by yourself and tell me if it's soluble or insoluble. I will go to the page. So NH4 3 times PO4, NH4 3 times PO4. So it's called the ammonium phosphate. NH4, PO4. Okay, there is no NH4, but there is PO4, right, in the insoluble one. So phosphates usually make insoluble compound, but we have to look at the exceptions. Compound of NH4 plus is there. It's an important exception. Yes, because we said earlier, anything that contains ammonium is actually soluble if you look at all the exceptions Ammoniums are always there. Ammoniums and the alkali metal. So phosphate, when it is with the ammonium, is actually soluble. Soluble. Okay, so that reviews that. So let's continue with, oops, things have moved. Calculation of concentration. So when you have a solution, you have more or less solute, right, in the solution. And so instead of saying, oh, it's a diluted solution or it's a concentrated solution, you can give it a value, and we call that the concentration. A concentration tells you how much solute you have per amount of solvent. And there are many, many kinds of units for concentrations. And the chapter goes through the mass per volume percent. There is also the volume per volume percent. But the mass per mass percent also exists. Molarity also we will study. So let's practice calculating the mass per volume percent concentration of a 250 milliliter solution containing 12.5 grams of an antibiotic. Yeah, let's answer that question first and answer the second one after. Well, no, I want, oops. Let's answer this one. What is the mass per volume percent of a 250 milliliter solution containing 12.5 grams of an antibiotic? So first thing, you want to bring the formula for the mass per volume percent. And this is given in your reference, so let me show it in the reference here. So for that, you need to go to page 1 of the reference here. The chapter 8 is using that space, the bottom of the page 1 of the reference. You have several formulas to calculate the mass per volume percent of a solution, the volume percent, the molarity, and then the dilution formula. Those 4 formulas are for chapter 8. And right now we will use the mass per volume percent. And I cannot copy that. Okay, mass per volume percent is grams of solute over milliliters of solution times 100. Okay, grams of solute over milliliters of solution. So mass, it doesn't have to be mass, volume percent. Oh, why is it doing that? Oh, like that. Oh, mass. Mass per volume percent. It's the grams of solute. Grams of solute. Well, this time we want it like that. Per milliliters of solution times times 100. Okay, so that's the formula. Let's see if we can directly plug in the values. So we have 250 milliliters of solution. Looks like it matches the denominator here. So let's put this here, 250 milliliters in the denominator solution. And in the numerator, we need the grams of solute. And here, the solute is the antibiotic, and we have 12.5 grams. So yes, we can directly plug in this in the formula of antibiotic. Times 100, right? So this was not asking any kind of conversions or anything. We directly had the milliliters of solution. You have to be careful when you read the text. Sometimes it will give you dissolved in 250 meters of water, for example. And if it's that, it tells you about the solvent. It doesn't tell you about the solution. So be very careful. Sometimes it will tell you the amount of solvent that you're adding your solute to. So in this case, you know, the solution is both the solvent plus the solute. So the volume of the solution would be the solvent plus the solute. Often case, it's the solution that is given, the volume of the solution. And then in this case, you don't need to add the volume of the, or the, well, here it's a mass, but if you had a volume, you don't need to add the volume of the solute. So let's do this in the calculator. 12.5 divided by 250 times 100. It's exactly 5 according to the calculator. How many sigfigs should we keep? So remember how 100 is an exact number, does never limit, right? Never limits. 12.5 has 3 and 250. So how many should we keep? Tell me just a number. So 250 has 2 sigfigs, the 2 and the 5. The 0 here is not significant because you don't see the dot. You don't see the decimal point. So that it makes the 0 not significant. So it's only 2 sigfigs there. So that means we need to show 2 sigfigs. And right now we have only 1 sigfig with the 5. So we need to say 0.0. And then the way we write the oh, it's doing this, but it shouldn't. Let me put this back into the oh, well, it's back. Okay. Ah, no, like that. So it's on one line, and we okay, like that. Okay, so that would be the calculation of the volume of the concentration in mass per volume. Then, so a concentration is telling you the amount of solute per amount of solvent. So there is 2 parts to a concentration unit. There is the description of the amount of solute and in a reference amount of solvent. And anything that is percent, like mass per volume percent or volume percent or mass percent, it's when it's percent, it means it's always for 100. And here, because it's mass per volume percent, it's per 100 milliliters of solution. The reference is 100 milliliters of solution. So when you read that 5.0 mass per volume percent, it means you have 5.0, and this applies to the solute. That's the quantity of solute per 100 grams of, and here it's per volume, so per 100 milliliters, sorry, not grams, milliliters of solution, right? It's per solution. So this number means, so let me rewrite this 5.0 mass slash volume percent means we have, and so because it's mass per volume, so it's grams of solute per 100 because it's a percentage, and per volume, so it's then milliliters per 100 milliliters of solution, right? That's how you want to read this number. This 5% by mass per volume means you have 5 grams of solute per 100 milliliters of solution. So then, well, okay, if you want to deliver 5 grams of antibiotic, what is the volume of solution that should be administered? Well, this answers the question, right? But actually, I should have looked at this before. Um, really, yeah, there's no point of doing a calculation, but you would want to do to use this as a conversion factor that has the 5 grams of solute, you know, equals 100 milliliters of solution. And let me change that because I really want to show you how. Let's say 8. If you want to deliver 8 grams of antibiotic, what is the volume of solution that should be administered? And so you would start with your given amount of 8 grams of antibiotics that you want to you know, deliver, times and then the conversion factor that comes from this concentration, where you will have, so the way to decide where things go, so it's the given is grams of antibiotics. So and here I should have said, let me put it slash antibiotic, because the antibiotic is the solute in this case. So we want to cancel the unit of grams of antibiotics. So this 5 grams of solute or antibiotic will go on the bottom so that we cancel the unit. So 5.0 grams of antibiotic on the bottom, and then the 100 milliliter of solution should go on top. Oops. Right, so I do this calculation. No, let me go back here. Okay. To show you how we can use those concentration as conversion factors. So in the calculator, you do 8 times 100 divided by 5, and it's 160. So it's the calculator answer, but it happens to be 2 sig figs here, the 1 and the 6, if I keep it like this, right? And here we have 2 sig figs in 5.0 and 2 sig figs in 8.0. So we will keep it like this, because the 100 here is exact. Whenever you use 100 from a percentage, it's always exact, never limiting. And here the grams of antibiotic would cancel, and you're left with milliliters of solution. It shows you the unit that is left, and it should be the unit you're looking for. And so if you want to deliver 8 grams of antibiotic, what is the volume of solution that you should administer? It would be 160 milliliters of solution. Okay, so that answers the second question. So let's continue with molarity. What is the molarity of a solution prepared by dissolving 10 grams of Na2CO3 in 850 milliliters of solution? Molarity. We have a formula for that. Let's look at that in the reference. Molarity, same page of the reference, first page, bottom of the page. Molarity, the definition is that it's the moles of solute over liters of solution. So molarity is moles of solute over liters of solution. So let me rewrite it here. Equals, and so it's moles of solute, and that's why, because it's moles of solute over liters of solution, it's used in chemistry a lot, because we count by moles, and so that's why it's a unit used in moles, but not really in like hospitals or pharmacies. They don't really use that. It's more like a chemistry unit. So it's moles of solute over liters of solution. And we have grams of Na2CO3 in 850 milliliters of solution. So the units are not the ones we need, right? You see how we need moles and liters, and we have grams and milliliters. So that means you will have to do some conversions before you can plug in the values into the molarity formula. Let's do the liters of solution first from this 850 meters of solution. Let's change that to liters. And actually, let's make it into a, so that we practice, you know, calculating using conversion. I lost my thing. What happens? So it's what was it? 850 milliliters. Why can't I do that inside? No, okay. Okay, I have to type it. Solution. So this is what we want to change, right? We want to change that into liters. So we will multiply by the fact that we have 1 liter, 1,000 milliliters in 1 liter. So here we have milliliters of solution as the given amount. So we want to put the part of the conversion factor that has the milliliters on the bottom. So the 1,000 milliliters will go on the bottom, and then the 1 liter of solution will go on top. And we can just keep it like this. So it's 850 divided by 1,000, and that's 0.8. And is the 0 significant here? Can you tell me yes or no? Is the 0 significant in 850 milliliters of solution? No, yes. It's not significant. There was no decimal point, so it's not significant, so I don't show it. So I keep it to sig figs. And sorry, it's liters. Liters of solution. So that's my liters of solution, so that's ready. And let's do now the 10 grams of Na2CO3. Can someone tell me how I change that into moles? What do I use to change grams to moles? What is the thing I use for that? To change grams to moles? No. It's not Avogadro number. Yeah. No, it's not. Let's look at the reference. It's not that. If you look at this is yes. If you look at the bottom of page 2 of the reference, we have grams. And so let's look at the first conversion map here, the one that says how to convert between particles, and moles and grams of a substance A, and that's what we have here. Substance A is Na2CO3, and we have grams of it, 10 grams, and we are asking for moles. Moles are not a number of particles. Be careful. Particles really refers to atoms and molecules, the particles. Moles, you know, in 1 mole you have 6.022 10 to the 23rd particles. It's above here at the Avogadro number. We don't need that. What we need is just between the grams and moles here, and it's the molar mass. So we need the molar mass of Na2CO3. And for this, we use the periodic table, right? So let's look at Na2CO3. So we will take 22.99. So 22.99 times 2. C plus carbon, so it's 12.01, plus 3 times 16 for the 3 oxygen. And we keep 2 decimal places, right? Because all the values were given with 2 decimal places, we are adding them. So we keep 2 decimal places. And what I have is 105.99. Did you get that too? So let's go back here. So Na2CO3 molar mass. (105.99 grams per mole), right? Please give the unit properly. It's grams per mole. Don't tell me molar mass. It's not enough. It's not a unit. The molar mass is the name for this, but it's grams per mole, right? So we have this, and we know that we can use this as a conversion factor to convert grams of Na2CO3 into moles of Na2CO3. So let's do that. Again, it's a conversion here that and we start with 10.0 grams of Na2CO3. Times the conversion factor comes from the molar mass. Here, because we start, the given amount is given in grams of Na2CO3. So we want to cancel the grams, and because the given amount here is always in the numerator, it's like this being, I can show that, it's like being above 1 as the denominator. So let's put 105.99 grams on the bottom, and that's grams of Na2CO3 over 1 mole of Na2CO3. And let's copy that. Okay. This way, the grams of Na2CO3 cancel, and we are left with moles. So the answer will be in number of moles of Na2CO3. In the calculator, you do 10 times, divided by 105.99, and it's 0.094348. So that's the calculator answer. The molar mass has 5 sig figs. The 1 mole is exact, never limits. And the given amount has, so can you tell me how many sig figs in the given amount? How many sig figs should we keep from the given amount? No. When you see the decimal point, it makes all the zeros significant. Yes. Right? It's 3, because you see the decimal point here. So everything is significant. So that's 3. So we keep 0.0. These are not significant. And so we start counting from 9, 4, 3. What comes after the 3 is a 4. So we keep the 3 and we drop everything after. And it's moles of Na2CO3. So that's our number of moles of Na2CO3. So now we are ready to do the molarity. And let's copy that here and continue. And so we are able now to plug in the values of moles and liters. So on top, it's going to be 0.0943. Actually, it's intermediate answer, and I should not have really rounded it. The liters, we have 2 sig figs, so that's okay. 0.85 liters, right? That's given there. And we have 2 sig figs in the liters here and 3 sig figs in the moles. So we will keep 2 sig figs in the end. So in the calculator, I still have my number and I will directly divide by 0.85 and it's 0.11099. Maybe if you do exactly 0. Let's see, because I didn't remove the number I had in my calculator, so I just continued. Yeah, it's almost the same, except here it's a 4, but let's write it like this. And let's do the rounding before I write the unit. So we said 2 sig figs. So 0 is not significant. We keep the 1, that's 2 sig figs already. What comes after the 1 is a 0, so we keep it like that. We do not, we keep it. And that's, let me write it like this. This is moles per liter, right? It's also written as 0.11 capital M. Capital M is the symbol for moles per liter. It gives the concentration in molarity. But molarity here, the capital M, you should see it as moles per liter. It's important because, again, if you have a calculation to do like above, where you need to use the concentration as a conversion factor, then you want to see that its meaning is that it's 0.11 moles of solute per liter of solution. That's how you should read this. It's 0.11 moles of solute per liters of solution. Okay, so that's the molarity. Do you have questions on, you know, all of this? No? So some more calculations of concentration, but this time from, well, I'll let you guess. How many milliliters of a 5.0 molar sucrose solution would be needed to prepare 750 milliliters of a 1.0 molar solution? That's not, there's no keyword there, unfortunately. So try to think about it. You have, well, you want to prepare 750 milliliters of a 1 molar solution. That's what you want at the end. But looks like you have a 5 molar sucrose solution and you want to have only a 1 molar sucrose solution. Does it ring a bell? What does it make you think of? How can you do that? You know, have a concentrated solution and end up with a more diluted solution, a less concentrated solution. Do you know how we call this? When we add solvent, just solvent, to a solution to dilute it, it's dilution, right? So this is a dilution problem. And let's go back to the reference here because we have a dilution formula. Page 1 of the reference packet, you have the dilution formula that says C1 times V1 equals C2 times V2. Very important formula here, C1 V1 equals C2 V2. The 1 refers to, you know, the stock solution or the concentrated solution, and the 2 means the diluted solution, the one that you added solvent to it and that, well, the one that you get from adding solvent and that is now diluted. So we'll use that formula. Because we are doing a dilution here. Formula is C1, you know, times V1 equals C2 times V2. And so the tricky part when you are using this formula is to give the proper value to the proper variable, right? So you have C1, you need to find what it is equal to C1. You need to find V1, you need to find C2, and you need to find V2. And so one of them will be missing. You will have three. You have the values for three of them, and one of them is missing, and that's the one you're looking for. So let's look at the text again. How many milliliters of a 5.0 molar sucrose solution would be needed to prepare 750 milliliters of a 1 molar solution? So the ones here refers to the stock solution, the concentrated solution, and the two here refers to the diluted solution, the one, the solution you get once you have done your dilution. So if you look at the text carefully here, so how many milliliters of 5 molar solution would be needed to prepare? So to prepare 750 milliliters of a 1 molar solution. So that's what you want at the end, right? You want this at the end. And so there is a volume. And so that's the volume you want at the end. So that will be your V2. That's V2. And the concentration at the end is that you want is 1.0 molar, right? And these go together. You don't want to split them. They go together. It's the diluted solution that you want at the end. And you can see this is more concentrated, right? 5 molar is more concentrated than the 1 molar. So that's the solution you start with. You always start with the more concentrated solution. And when you're diluting, you are making it less concentrated. You're adding a volume of solvent, and this decreases the concentration. So the 5 molar is the concentration of the solution you start with, and how many milliliters? So it looks like we are looking for V1. How much of the stock solution or the concentrated solution should we take, and then add water to it up to the 750 milliliters mark. And so we are looking for V1. So you want to change your dilution formula such that V1 is, by itself. And so you, yeah, so C1, well, I should do this first. C1, V1, oops, no. Okay, C1, V1, C2, V2. So how do I solve for V? To have V1, I mean to have V1 by itself, I need to get rid of C1. So what do I do to my equations so that I get rid of C1 on the left side? What about dividing by C1 on both sides? If you divide by C1, let me make it subscript. C1, you will get rid of the C1 on the left side. And what you do on the left side, you have to do it on the right side so that it's still equal. Otherwise you would change the equality, right? So what you do on the left side, do it on the right side. And so that means when you are done with this, it's that V1 is equal to, oh, I'm still in there. V1 sorry, those subscripts are taking some time. V1 equals C2 V2 divided by C1. And so let's plug in the values now. So C2 is 1.0 molar times V2 750 milliliters. All of this divided by C1 is 5.0 molar equals, so in the calculator it's 1 times 750 divided by 5, and the calculator answer is 150. So the molarities cancel, right? The capital M cancel, and so you're left with milliliters here. So about sig figs, how many sig figs in 1.0? Can you tell me that? 1.0, how many sig figs? Yes. And then 5.0 is the same. And then 750 meters, how many sig figs? Yeah. Still 2, right? Because there is no decimal point. So it's all 2 sig figs. So then 150. Here we have the 1, we have the 5, it's 2 sig figs. And we don't show the dot because it's 2 sig figs like that. So that would be the volume of stock solution or concentrated solution that you would take. So the way we do this is usually we take what we call a volumetric flask, that are special flasks that are calibrated. You would choose a flask that has a volume of 750 milliliters. Hopefully, yeah, they should exist. So you take a flask that is calibrated to hold 750 milliliters precisely. You place in there the 150 milliliters of the stock solution of your 5 molar sucrose solution, the one that is very concentrated. And then you fill up the flask with water up to the 750 milliliter mark. You swirl or mix it, and there you go. You have your diluted solution, 1 molar, and you have 750 milliliters of it. So that's how we do dilutions. Okay, so a beaker contains 2 compartments, A and B, and so here see how it's A and B. A is the left side, B is the right side, with equal volumes of solution. It's not the same solution on both sides, but you have the same amount of solutions on both sides. And they are separated by a semipermeable membrane. So what is a semipermeable membrane? It lets go of typically small particles and does not let bigger molecules go through, right? It's selectively allowing smaller molecules and not large ones. And in particular here, it does not let the solute, the red dots here represent the solute. It does not let the solute go through. Only the blue, the water, can go through. So the solute, they cannot move from one side to the other. And so after a while, you see that the levels of the 2 solutions have changed according to the second beaker. So the second beaker here to the right, that says T after equilibrium, because they slowly move, and then it stops at that point where you have the left solution A, at a higher level than the solution B now. So that tells you water has moved from B to A. It has moved from the right to the left side of the semi-permeable membrane. And again, it's the water who moves because the solutes, the particles, the red dots, they cannot move across that semipermeable membrane. And so what we have is on the, well, we don't know if it's on the left or on the right, but we have a solution that is 0.20 molar Na2SO4, and the other solution is 0.30 molar glucose. So that's the two solutions, A and B, but we don't know which one is A and which one is B. But we know how they have behaved after a while. And so this movement of water, you know, going from right to left here, you can see on the left side there is more red dots, right? So that tells you it's more concentrated. So you have solution A that is being more concentrated than solution B. And because the solute, they cannot, you know, equalize, then it's the water that will try to equalize the concentrations by moving from B to A, because water will go from low solute concentration to high solute concentration to try to, you know, equalize the concentrations. And you can see on the beaker on the right, it looks more the same on both sides now. And that's because water has moved to equalize the concentrations. And so we need to decide which solution is A and which solution is B. And so basically, we know A is more concentrated than B, right? So let's look at those two solutions and see which one is more concentrated. I have to add that osmosis is what we call a colligative property. Yeah, so let me write this. Osmosis is a colligative property, which means it depends on the number of solute particles, but not on the identity of the solute. Right? What matters for osmosis, the reason why water moves, it's because it's more concentrated. There is more particles per unit of volume on the right side than, sorry, on A, the solution A, than B, right? And it doesn't matter if the solute are not the same kind on both sides. What matters is that the numbers of particles is different, right? So we need to decide, and which one is more concentrated, in the sense that which one has more solute particles per unit of volume. So you have to take into account the formula and the type of solute you have. And so let's look at this one first. 0.20 molar Na2SO4. This is an ionic compound, right? It's made of sodium and then the sulfate ion. And it's soluble, right? We could check in the solubility rules, but that's, well, actually we know because it's made of sodium here. Sodium is always making, it's an alkali metal, it's always making soluble compound. So it's soluble in water and it dissociates into ions in water. So we need to find what kind of ions it dissociates and how many ions it dissociates into. So can you tell me the first ion that comes from Na2SO4? So Na, what kind of ion does it make when it's an ion? So give me the symbol for sodium when it's an ion. Na, what is its charge? Yes. Right? We know this because, and let me make it like this to show that it's Na in solution. How do we know this? It's because if you look at the periodic table, Na is part of the 1A group. So it's a metal, and so it will make a Na plus ion, right? Group 1A, so plus 1, right? So we know its formula from the position in the periodic table. SO4 is different. SO4 you would look at the list of polyatomic ion, because that's a polyatomic ion, right? It's made of two nonmetals. And here you will want to look at SO4 and find its charge. You can also find the charge from the compound formula, but let's look here. SO4 is two negative charges, right? So let's use those symbols. SO4, -2, aqueous. So be careful, the 4 is a subscript. It means you have 4 oxygen per sulfur. And the 2 minus is the charge of this whole thing, SO4, right? Is it correct like this? How many sulfate do we have and how many sodium ions do we have when Na2SO4 dissociates? Yeah, so it's too complicated to answer. So we have 2 sodium, right? You see that in the formula, there's a subscript of 2 for sodium, right? There's Na2 here. That 2 tells you you have 2 sodium per sulfate, 2 Na plus and 1 SO4 -2. And this way, those 2 sodium will make 2 positive charges in total, and they will cancel those 2 negative charges from the SO4, right? So that's why you need 2 sodium per sulfate to make this neutral formula. So 0.20 molar Na2SO4 dissociates into 2 Na plus and 1 SO4. So 3 particles, right? 3 particles per formula. So that means the molarity is not really 0.20 molar if you count the number of solutes particles. What you do is you take that concentration and you multiply it by the number of particles, 3 ions. In this case, it's ions. And that is really seen for, from the point of view of osmosis, it's seen as a 0.60 molar solution, right? And we call this osmolarity, by the way. Let me just type it here, but it's not in your lecture. But that means it's a 0.60 osmolar solution. You will see that in the lab, so that's why I need to start to talk about it. So it's a 0.60 osmolar concentration. So now let's look at the other one. Is it more concentrated or not? That's glucose. That's its molarity. So glucose, it's a bigger molecule made of carbons. It's a cycle of 6 carbons surrounded by H's and OH. So a lot of bonds with H and OH. It does, when it's dissociating, it's not dissociating, I should say. Dissolves in water as glucose. It stays the same. It stays as one big molecule that is neutral and dissolves in water as a glucose molecule. So it's one particle here per formula, right? It's one particle and it stays the same. So that means if we count in osmolarity, which means 0.30 molar times one molecule, and it's going to be 0.30 osmolar. So it stays, the osmolarity is the same as the molarity. So now if we look at the two, which one is more concentrated? Can you tell me, is it, so tell me first or second? So first is the 0.20 molar Na2SO4 and the second is the 0.30 molar glucose. So which one is more concentrated? Is it the first solution or the second solution? Yes, the first is more concentrated in solute particles per unit of volume. Um, so because it's 0.60 osmolar versus only 0.30. So even though the molarity of glucose, the glucose solution looks like it's a higher number, actually the osmolarity is smaller because it does not dissociate into multiple particles, it stays as one molecule. And so that's very important to pay attention to that. So that means solution A is, so we said A is the more concentrated. We can see from the red dots, it has more solute. So solution A is the 0.20 molar Na2SO4, and solution B is the 0.30 molar glucose. Right? We know this because the Na2SO4 has more particles per unit of volume than the 0.30 molar glucose. So the water will want to go from low solute concentration to high solute concentration to try to equalize the concentration. So that's what osmosis is about. And so let's finish this. It's also about osmosis, but this problem introduces new terms: isotonic, hypotonic, and hypertonic. And that's the way to classify substances depending on the reference substance. And the reference substance here will be the intracellular fluid of your red blood cell. So let's say you have that red blood cell placed into a 1.8% mass per volume NaHCO3 aqueous solution. What happens to the red blood cell? Solutions isotonic, so that have the same tonicity as body fluids, right? We are made of a lot of fluids in our body, and we know what is the concentration, if you will, of our body fluids. And it's translating into either 0.92% mass per volume percent NaCl solution, or you can see it as a 0.15 molar NaCl solution, or a 5% mass per volume glucose solution, right? And you will compare what you put your red blood cell in with the concentration that matches the one you're given, right? This 1.8% mass per volume of NaHCO3, you want to compare it to something that will be in a mass per volume percent. So you will not use this one. So your red blood cell is either made of this one or that one. But to decide between the two, you need to look at the type of solute here, or the type of solution. And this is an ionic compound, so it's more like the NaCl than the glucose. So you want to compare them with this one. So what you want to see is that your red blood cell has this solution of 0.92% mass per volume of NaCl inside, and you're placing that red blood cell into a 1.8% mass per volume of NaHCO3. And you want to decide if which one will be more concentrated, if one is more concentrated. And so that will decide if the water will move out of the cell or move in the cell by osmosis, right? And ideally, you want them to be isotonic, the solution, so that the red blood cell stays healthy. So let's compare these two concentrations. So 1.8% mass per volume of NaHCO3. Again, what matters is what kind of solute particles does it dissolve into when it's in solution, this NaHCO3. So it's an ionic compound because we have sodium there, it's a metal, and then all of this are non-metals. And maybe you recognize something here? if you don't, then go to your list of polyatomic ions. If you look at the list of polyatomic ions, in the middle here, you will see in the row for carbon, HCO3 negative 1 is called the hydrogen carbonate or the bicarbonate ion. So this is the ion you have with the sodium in your NaHCO3. You know, it's sodium bicarbonate or sodium hydrogen carbonate. You can call it both ways. So that's one of the ions, and then the other will be the sodium. So this dissociates into, and we have again Na+, so I'm not going over this one, and HCO3 negative 1. Right, so those charges are superscript, only the one negative charge here, and the 3 is a subscript. Let me this board so we see that better. So NaHCO3 dissociates into Na plus and HCO3 minus. 2 particles, right? 2 particles per formula. So that means 1.8% here times 2 particles or 2 ions equals 1.8 times 2, 3.6%. So it's like a 3.6% as far as number of solute particles, right? And if we look at the 0.92%, you know, M/V, oops, NaCl dissociates into Na plus, right? You recognize Na plus and Cl minus, right? Hopefully by now you recognize NaCl easily and know that it's made of Na plus and Cl minus. So 2 particles. 2 particles. So that's the same number of particles. So you take its percentage times 2 ions, and that's going to be so 0.92 times 2, 1.84. 1.84. So which one is more concentrated? Then it's the NaHCO3. There's more solute particles per yeah. Second one. Did I do some? Yeah. No, it's correct like that, right? So the more concentrated is the NaHCO3 solution, right? So that means 1.8% NaHCO3. Oops, hold on. Is more concentrated than or I should say it's more concentrated than 0.92% NaCl, which is your red blood cell, right? Intracellular fluid. So then the water will want to move from the low concentration to the high concentration. So here it will move from inside the red blood cell out. So water will move out of the red blood cell. It will move out, and so the red blood cell will shrink. Right, the water will move out, so the volume of the red blood cell will shrink. It will shrink, and we call that it is called crenation. You don't have to remember this, but this is called crenation, when the red blood cells are misshaped due to the fact that water moved out. And actually, what I wanted to say is there is a name for that. It's hypotonic or hypertonic or isotonic. So here we found that the solutions are not isotonic, right? This 1.8 NaH03 is not isotonic. It's more concentrated than that. So we call this. So can you tell me, do you know if it's hypertonic, hypotonic, or isotonic to the other solution? If you've learned that or not. So it's more concentrated, so yes, we say it's hypertonic. Is hypertonic to the 092 NaCl or the red blood cell. So that's how we classify, you know, isotonic, hypertonic, or hypotonic solutions. It's always to a reference solution. I know it's a bit complicated, and the lab 6 is all about this, so there will be much more practice for this. The only thing is that the homework and the quiz are due tonight, so you need to have seen that still.